For the last part of Chapter 3, let's do some practice problems. We're going to revisit the idea that road salt is composed of both sodium chloride and calcium chloride. Looking at freezing point depression, we noticed that sodium chloride was much more effective at lowering the freezing point than calcium chloride. Therefore, one might think that you would use only sodium chloride. However, road salt is a mixture, and part of that has to do with the enthalpy of solution. So we're going to compare what happens when 10 grams of sodium chloride and later 10 grams of calcium chloride are dissolved into cold rain. We'll start with 10 grams of sodium chloride on the road reacts with 90 mils of cold rain at 5 degrees Celsius. The heat of solution of sodium chloride is plus 3.88 kilojoules per mole, and we're given the specific heat of the water. We want to know what is the final temperature of the rain. First, please note that the heat of solution of sodium chloride is positive. Therefore, it is an endothermic process. So when sodium chloride dissolves, it requires heat. This means it is going to lower the temperature of the water. So we're going to treat the sodium chloride dissolving as the system and the water as the surroundings. That means the heat of solution of sodium chloride is equal to the negative heat of solution of water. For the heat of solution of sodium chloride, we can use N delta H. And for the heat of water, we can use minus MS delta T. So for sodium chloride, we just have to take our 10 grams of sodium chloride, divide by the molecular weight, and multiply by the enthalpy of solution to get our heat of solution in units of kilojoules. For our water, we have 90 mils of water, which we can assume is 90 grams of water, times the specific heat of the water. Our goal is to find the final temperature of the rain, so that is the variable I don't know, TF. But I know the initial temperature of the rain is 5 degrees Celsius. So now it's just a matter of solving the math, except for one small detail. You notice that the heat of solution for water is going to be in units of joules. So let's make sure we convert from joules to kilojoules so that we are setting both sides equal to each other in the same units. When I multiply through the left side, I get 0.6639 kilojoules. The right side, I'm going to have to take these, multiply them, and distribute the values into both TF and the minus 5 degrees Celsius. And you will wind up with negative 0.3762 times the final temperature in units of kilojoule per degree Celsius plus 1.881 kilojoules. So it's a simple matter of solving the math and determining what the final temperature is equal to. We will be able to answer this question to 3 sig figs. Now let's look at the calcium chloride. Again, it's the same gram amount and the same setup. Q solution equal negative Q water, or N delta H equal minus MS delta T. So I will figure out my moles of calcium chloride, and you notice this time the heat of the solution is negative, so it is exothermic. That means calcium chloride releases heat when it dissolves. The water side stays the same as before, and of course make sure you convert it to units of kilojoules. So I'm pretty certain you can use the same process and solve for T final, and I trust you'll find that this value for calcium chloride is much higher than it is for sodium chloride. Now let's look at 3 different ways heats of formation can be calculated. This is my version of 3 chemists walk into a bar, except they walk into a lab. to find the enthalpy of formation of acetaldehyde. Chemist 1 wants to use bond dissociation energies to figure it out. So what is the balanced formation reaction for acetaldehyde? I trust you remember that formation reactions are from elements in their standard state. So I hope you know the standard state of carbon is a solid. The standard state of hydrogen is a gas as H2. And the standard state of oxygen is also a gas. I hope that will help you figure out the answer. In the second part, now that we have the formation reaction, we actually need to figure it out. So if I go back here now, I trust you will recognize that the formation reaction is right here. Answer D. So now I need to use this reaction right here in the next part of my calculation. So moving back to question 3b, what we want is to use the reaction shown here to get the enthalpy of formation of acetaldehyde. The only problem is that bond dissociation energies require everything to be in the gas phase. So what we're going to have to do is calculate this reaction with carbon in the gas phase and then make a correction using Hess's law to figure out the reaction we actually want where carbon is in the solid phase. So remember that the reaction is bonds broke minus bonds formed. So what I can see is that I am going to break 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen double bond. Those will be the bonds that I break. The bonds that I form, if you look at my compound here, it appears that I have 4 carbon-hydrogen bonds and a carbon-carbon bond and 1 carbon-oxygen double bond. So you need to, ignoring this one of course, substitute in these values. So you can solve this value and get delta H for this reaction right here where carbon is in the solid phase. Now, once you have that value, you need to do a slight correction. And to do that, we're going to use Hess's law. So what we're going to do is we will have a value we just calculated for delta H here, and we will add it to 2 times the transformation of 2 moles of carbon solid to 2 moles of carbon gas. You notice these will cancel out. And of course, that value is 2 times 716.7 kilojoules. And when we're finished, we will get to the reaction we want with the carbon in the solid state. So that is how the first chemist would solve the value. The second chemist wants to use heats of formation in the combustion reaction to calculate it. So, what is the balanced combustion reaction for acetaldehyde? And I hope you think about it and realize that when you combust something, you react it with oxygen to make CO2 and water. And we are doing this at 298 Kelvin, because that's where generally heats of formation are. So please consider that the water has to be in a state at room temperature. So I hope you came up with this particular reaction. So I hope you realize that we've been given the enthalpy of combustion, and that will be equal to the heat of formation of products minus the heat of formation of reactants for the combustion reaction. So we can set negative 1167 kilojoules equal to the enthalpy of formation of 2 moles of CO2 gas and 2 moles of H2O liquid minus our unknown, which is the enthalpy of formation of acetaldehyde gas, minus 5/2 the enthalpy of formation of oxygen, which is, of course, 0. So simply solving for that will give us our answer. As in all jokes, the last chemist is the most interesting, and chemistry likes experiments and uses bomb calorimetry. So, when 2.633 grams of acetaldehyde was burned in a bomb calorimeter containing 4,000 grams of water, the temperature of the water rose from 22.62 to 26.64 degrees Celsius. The specific heat of water is given. We want to know what is the enthalpy of formation of acetaldehyde. So, remember that when you are in a bomb calorimeter, we are getting the energy of combustion, not the enthalpy of combustion. And our problem seems to indicate that the water is the most important part of the calorimeter. So, whatever the energy of combustion of this reaction is, it is equal to the negative ms delta T change of the calorimeter. Because once again, the reaction is our system, the water is our surroundings. So first, we need to substitute in our values for the water. So we have minus 4,000 grams times the specific heat of water of 4.18 joules per gram degrees Celsius multiplied by the final temperature of 26.64 minus the initial temperature of 22.62. Multiplying all this out gives us a value of minus 67.214 kilojoules for 2.633 grams of acetaldehyde. So we, of course, need to get this to kilojoules per mole of acetaldehyde. So we can take 2.633 grams of acetaldehyde and divide it by 44.06 to give us 0.059759 moles of acetaldehyde. Now our job is to get it in kilojoules per mole. So we'll take our initial answer, divide it by the moles, and we will get delta E combustion per mole of acetaldehyde burned. Now, if you're thinking about previous problems, you'll say to yourself, okay, but I don't need energy of combustion, I need heat of combustion. So now I need to correct this for the moles of gas that add to the total energy of the reaction in order to get just the enthalpy. So I will remind you that delta E is equal to heat plus work, or delta H minus delta NG RT. So if I want to get the enthalpy of combustion, I have to take the energy of combustion and add delta NG RT in order to solve for that value. So you notice that I have 2 moles of gas formed, and incoming I subtract 1 mole of gas for the acetaldehyde and 5½ moles of gas for the oxygen, and my value of delta NG is equal to minus 1.5 moles of gas. So now I have delta H of combustion is equal to the value I got for delta E, which I hope you got the same, minus 1,124.75 kilojoules. So my delta NG of minus 1.5 times 8.314 joules per Kelvin mole times 298 Kelvin. And also don't forget to divide by 1,000 to get this value in kilojoules. Together, this will give us an enthalpy of combustion of minus 1121.0 kilojoules. And now, of course, I need to treat this exactly like the previous problem. I have a value for delta H of combustion, and I can set that equal to the heat of formation of products minus the heat of formation of reactants, and solve for the heat of formation of acetaldehyde. So I'm sure you want to check your work. These are the values I got. With bond dissociation energies, chemist 1 got minus 245. Using a literature value of the enthalpy of combustion, chemist 2 got 192, and chemist 3 with their experiment got minus 237. So you can see they're in reasonably close agreement. If you actually go and look at the National Institute of Standards tables, you'll find out that sometimes there is a slight amount of disagreement on the heats of formation of materials.